Find somewhere comfortable tonight, wherever you are, lying down, curled up, somewhere quiet in the dark. You don't need to hold on to any of this. You don't need to remember a word. The ideas will arrive on their own, like light from very far away, and you can let them pass through you and go again. We are in no hurry here. The night is long and patient, and so are we. If today was hard, you can set it down now. Whatever you carried through the hours, the weight of it, the noise of it, none of it is required in this room. This hour belongs to something older and quieter than any of that. We are going to travel tonight. Not anywhere you have to try to reach. Just outward, slowly, into the dark between the stars, into the extraordinary story of how the universe itself is moving. Space is stretching. Space is stretching. Right now, as you rest, as your breathing slows, the galaxies are drifting apart, not because anything is pushing them, not because they are flying through some vast empty room. The fabric of space, the very medium in which everything exists, is expanding in all directions, carrying light and matter gently apart, unhurried in the deep and ancient dark. That is what we are going to explore tonight. How we came to know this, what it actually means, where it all began, and where it is all going. And somewhere along the way, perhaps you will find that the immensity of it all is not frightening, but restful. That being small inside something this vast is not isolating. That it is, in its own quiet way, a kind of company. So settle now. Close your eyes if they are not already closed. The words will find you. For most of human history, the night sky was a fixed thing, permanent, reliable. The stars rose and set with the seasons, and whatever else changed in a human life. Kingdoms, harvests, the faces of the people you loved, the stars remained. It was natural then, almost inevitable, that the universe itself came to be imagined as eternal and static. A stage, not a story. Something that had always been more or less as it was and would continue to be. Even Albert Einstein believed this when he completed his general theory of relativity in 1915, a framework so precise and so sweeping that it rewrote the rules of gravity, space, and time. He found that his own equations refused to cooperate with the static universe he assumed must exist. The mathematics kept insisting that space could not simply sit still. It wanted to expand, or it wanted to contract. It would not hold steady. So Einstein did something remarkable and, in retrospect, a little poignant. He introduced an extra term into his equations, a kind of mathematical counterweight, a repulsive force built into the fabric of space that would exactly balance the tendency to collapse or grow. He called it the cosmological constant. He added it not because the physics demanded it, but because the answer it produced matched the universe he already believed in. A universe at rest. He was wrong, and the path toward knowing he was wrong began not in a grand institution, not with a celebrated name, but in the dry hills of Arizona, in the quiet, methodical work of a man named Vesto Slipher. Lowell Observatory sits on a mesa above Flagstaff, at an elevation high enough to escape much of the atmospheric blurring that plagues lower telescopes. It was built by a wealthy amateur named Percival Lowell, who was convinced, incorrectly as it turned out, that the planet Mars was crisscrossed by canals dug by an intelligent civilization. Lowell had grander ambitions for his observatory, but it fell to one of his staff astronomers, the quiet and meticulous Vesto Slipher, to do the work that would eventually change cosmology. Slipher was not a flashy scientist. He was careful, patient, and deeply skilled. In 1912, he turned the observatory's main telescope toward one of the fuzzy spiral patches of light that dotted the sky, objects then known as spiral nebulae, which most astronomers assumed were clouds of gas within our own Milky Way, perhaps the birthplaces of new solar systems. He was interested in their spectra. A spectrum, in this context, is what you get when you split light apart into its component wavelengths, the way a prism spreads white light into a rainbow. Every element emits and absorbs light at very specific wavelengths, specific colors, producing a pattern of lines in the spectrum as distinctive as a fingerprint. By reading those lines, you can identify what a distant object is made of, and, crucially, you can detect whether those lines have been shifted. When a source of light is moving toward you, the waves of light it emits are compressed slightly, pushing the spectral lines toward the blue end of the spectrum. When it moves away, the waves are stretched and the lines shift toward the red. This is called the Doppler effect, the same principle that makes an ambulance siren pitch higher as it approaches and lower as it recedes. Slipher was looking for this shift in the spiral nebulae. What he found in the case of the Andromeda Nebula was a blue shift. Andromeda was approaching. But as he turned to other spiral nebulae over the following years, the picture changed. Almost every other one he measured showed a redshift, and not a small one. These objects were receding at speeds that seemed, by the standards of the day, almost impossible. Some were moving away at hundreds of kilometers per second, a few at over 1,000. No known star or gas cloud within our galaxy moved anything like that fast. By 1914, Slipher had measured the spectra of 15 spiral nebulae. 11 were moving away. The velocities were extraordinary. He presented his findings at a meeting of the American Astronomical Society that year, and the audience apparently gave him a standing ovation, one of the very few times in the Society's history that had happened. They recognized that something important had been found, even if no one quite knew what it meant yet. The missing piece was distance. To know what these redshifts were telling you about the universe, you needed to know how far away these objects were, and at the time, no one could measure distances beyond a few thousand light-years with any reliability. The spiral nebulae might be nearby. They might be unimaginably far. Without a way to know, the redshifts were suggestive but not conclusive. That distance problem had already been quietly solved, though not yet applied to the question. The solution came from a woman working at the Harvard College Observatory, a place that in the early 20th century employed a number of women as human computers, hired to analyze photographic plates of stars, doing work that was painstaking, underpaid, and in several cases scientifically transformative. Henrietta Swan Leavitt was one of them. She was assigned to study a class of stars called Cepheid variables, stars that pulse, brightening and dimming in a steady rhythm over periods of days or weeks. These pulsations are driven by a cycle in the star's outer layers. Helium in the atmosphere alternately absorbs and releases radiation, causing the star to expand and contract like a slow, steady heartbeat. Leavitt was cataloguing Cepheids in a nearby galaxy called the Small Magellanic Cloud, visible from the southern hemisphere as a faint smudge of light. Because all the stars in the Small Magellanic Cloud were at roughly the same distance from Earth, they were all part of the same galaxy, so any differences in their apparent brightness reflected real differences in their actual brightness. Leavitt could compare them fairly. And what she found, published in 1912, was a relationship of extraordinary precision. The longer the period of a Cepheid's pulse, the more days it took to complete one brightening and dimming cycle, the more luminous the star actually was. A Cepheid that pulsed over 30 days was genuinely, intrinsically brighter than one that pulsed over 3 days by a predictable and consistent amount. This was a ruler, a cosmic ruler. If you found a Cepheid variable anywhere in the sky and measured how long its pulse took, you immediately knew how bright it truly was. Then, by comparing that true brightness to how bright it appeared from Earth, you could calculate its distance with precision. The dimmer it appeared relative to its known true brightness, the farther away it must be. Leavitt had given astronomy its first reliable method for measuring the universe beyond our own neighborhood. She received little recognition for this in her lifetime. She died in 1921 before the full implications of her discovery were understood. There is evidence that she was being considered for a Nobel Prize when she died, though the Nobel is not awarded posthumously. The person who applied her ruler to the spiral nebulae was Edwin Hubble, working at the Mount Wilson Observatory in California, which had recently been equipped with a 100-inch reflecting telescope, at that time the largest and most powerful in the world. Hubble was ambitious, competitive, and gifted. He spent long, cold nights at the telescope photographing the Andromeda Nebula and other spiral objects, searching the photographs for Cepheid variables. He found them. He measured their periods. He applied Leavitt's relationship, calculated their distances, and arrived at a number that settled the debate about what the spiral nebulae were once and for all. Andromeda was not a gas cloud within our galaxy. It was nearly 1,000,000 light-years away, far beyond any boundary of the Milky Way. It was a galaxy in its own right, a vast collection of hundreds of billions of stars as large as our own. The spiral nebulae were island universes, separate and remote beyond anything previously imagined. And then Hubble did something more. He combined his distance measurements with Slipher's velocity measurements, the redshifts that had been accumulating for over a decade, and looked for a pattern. He published his results in 1929, and the pattern was unmistakable. The farther a galaxy was, the faster it was receding. Not randomly faster. A galaxy twice as far away was receding twice as fast. 3 times as far, 3 times as fast. The relationship was clean, linear, and universal. This was not a coincidence. It was not a local peculiarity. It was, as Hubble recognized, a law written into the structure of the cosmos itself. Every galaxy was moving away from every other galaxy, and the rate of that recession scaled precisely with distance. The universe was not static. It was not eternal and unchanged. And the implications of that single observation would take decades and the work of many minds to fully understand. Einstein, when he learned of Hubble's findings, reportedly called the cosmological constant, the fudge factor he had inserted to hold the universe still, the greatest blunder of his life. The universe had been trying to tell him something, and he had refused to listen. There is a temptation, when you first hear that the universe is expanding, to picture it the way you might picture an explosion. Galaxies flung outward through empty space, like debris from a blast, rushing away from some central point where the Big Bang occurred. It is a natural image. It is also wrong in a way that matters deeply, because getting it right reveals something far stranger and more beautiful about the nature of reality. The galaxies are not, in general, moving through space. Space itself is moving, or more precisely, space itself is growing. The distinction is not merely philosophical. It changes what expansion actually means, how it can be measured, and what the ultimate fate of the universe might be. To understand this, you need to understand something about what Einstein's general theory of relativity actually says. Not the equations, just the core idea, which is genuinely accessible and genuinely profound. Before Einstein, space and time were thought of as separate things. Space was the 3-dimensional stage on which events occurred. Time was the independent clock that ticked uniformly in the background. Newton's physics depended on this picture. Space was fixed, time was absolute, and objects moved through both. Einstein showed that this picture was incomplete. Space and time are not separate. They are woven together into a single 4-dimensional fabric. 3 dimensions of space and 1 of time, interlocked in a way that means you cannot change one without affecting the other. This combined fabric is called space-time. When you move through space, you also move through time, and the faster you move through space, the more slowly time passes for you. The two are genuinely linked. Now, What makes general relativity specifically about gravity is what Einstein proposed about the relationship between matter and this space-time fabric. Massive objects do not simply sit in space-time. They warp it. They curve it. The Earth curves the space-time around it, and what we experience as the Earth's gravitational pull is actually the effect of that curvature on everything nearby, including light. The moon is not being pulled toward the Earth by a mysterious force acting at a distance. It is following the straightest possible path through curved space-time, and that path happens to be an orbit. This is the central image of general relativity. Mass curves space-time, and curved space-time tells matter how to move. But the theory says something more. It says that space-time itself, the fabric, is a physical thing, not a fixed, rigid stage, but something flexible and dynamic. It can curve, it can warp, and, crucially, it can stretch. The fabric of space can expand, with the expansion carrying everything embedded within it, along for the ride. This is what is happening to the universe. Space is not a container into which the galaxies are moving. Space is a medium that is itself growing, and the galaxies, those that are not gravitationally bound to one another, are being carried apart by that growth, the way dots drawn on the surface of a balloon are carried apart as the balloon is inflated. That balloon analogy is worth dwelling on for a moment, because it is genuinely useful, even if it has limitations. Imagine a rubber balloon with small dots drawn all over its surface. As you blow the balloon up, every dot moves away from every other dot. No single dot is at the center of the expansion. From the perspective of any one dot, all the others are receding, and the farther away a dot is, the faster it appears to recede. Because there is more rubber between them, all of it stretching. This is exactly the pattern Hubble observed. The farther a galaxy, the faster it recedes, not because the distant ones are moving faster through space, but because there is more expanding space between us and them. The limitation of the balloon analogy is that a balloon is a two-dimensional surface expanding into three-dimensional space. You can imagine the outside of the balloon, the space it is inflating into. The universe does not work like this. Space is not expanding into anything. Space is all there is, and it is simply becoming larger, in the same way that the surface of the balloon becomes larger without needing any space outside itself to expand into. The analogy captures the pattern of recession correctly, but misleads about the geometry if you take it too literally. What does it actually mean, then, for space to expand? Here is the precise way to think about it. Take two galaxies separated by some distance. Neither galaxy is moving through its local space. Both are, in a sense, sitting still. And yet the distance between them is increasing. The space between them is stretching. New space is appearing between them continuously, as if the fabric is being gently pulled in all directions at once. The galaxies are not racing apart. They are being carried apart without moving. This distinction has a real consequence for something called the speed of light. Einstein also showed, in his earlier theory of special relativity, that nothing can move through space faster than light, roughly 300,000 kilometers per second. This limit applies to objects moving through space. Space can grow at any rate, and at large enough distances, the space between two galaxies can be expanding so rapidly that light from one cannot reach the other. Not because the light is slow, but because the space it must cross is growing faster than the light can traverse it. This is not a violation of any physical law. It is simply what expansion at large scales implies. Now, where did the idea that space could expand actually come from theoretically? It came from Einstein's own equations, just not from Einstein himself. In 1922, a Russian mathematician named Alexander Friedmann was working through the full implications of general relativity applied to the universe as a whole. He made a simplifying but physically reasonable assumption that the universe, viewed at the largest scales, looks more or less the same in every direction and from every location. No special places, no preferred direction. Just a smooth, uniform distribution of matter and energy. Under this assumption, he solved Einstein's equations and found that a static universe was not a stable solution. The equations described a universe that was either expanding or contracting. The static solution that Einstein had forced into existence with his cosmological constant was, in Friedman's analysis, unstable, like a pencil balanced on its point. Any tiny perturbation would cause it to evolve. The universe, the mathematics said, must be dynamic. A few years later, in 1927, a Belgian Catholic priest and physicist named Georges Lemaître arrived independently at the same conclusion. Lemaître was a remarkable figure, a man who saw no conflict between deep religious faith and rigorous science, and who pursued both with equal seriousness. He solved Einstein's equations, found expanding solutions, and went one step further. He connected the theoretical expansion to Schleifer's observational data on receding nebulae and estimated a numerical value for the rate of expansion, what we now call the Hubble constant, though Lemaître calculated it first 2 years before Hubble published his observational confirmation. For this reason, the law describing the relationship between distance and recession velocity is now officially known, by decision of the International Astronomical Union, as the Hubble. Lemaître then followed the expansion backward in time. If the galaxies are all moving apart now, then in the past they must have been closer together. Further back, closer still. All the way back, the entire observable universe must have been compressed into an extraordinarily small, extraordinarily hot, extraordinarily dense state. Others, less charitably, called it the Big Bang, a term coined by the astronomer Fred Hoyle, who actually disbelieved the theory and used the phrase somewhat mockingly. The name stuck anyway. What Friedman and Lemaître had done was remarkable. Working from pure mathematics and the principles of general relativity, they had derived the expansion of the universe before anyone had observed it. The theory arrived before the data. When Hubble published his observational results in 1929, he was not discovering something new so much as confirming something the equations had already said. Reality was catching up with the mathematics. Einstein, upon hearing of Hubble's results and understanding their implications, visited Mount Wilson Observatory and looked through the great telescope himself. He removed the cosmological constant from his equations. The universe was expanding. It had always been expanding. The static universe he had believed in and had distorted his own theory to accommodate had never existed. The fabric of space was growing. And it had been growing, the equations now suggested, since the very beginning of time. There is something quietly astonishing about the fact that we can know anything at all about objects billions of light years away. We cannot visit them. We cannot send probes. We have no way to touch or sample anything beyond the edges of our own solar system. Everything we know about the distant universe arrives in the form of light, electromagnetic radiation, streaming across the void for millions or billions of years before reaching our instruments. And from that light alone, if you know how to read it, you can extract an extraordinary amount of information. The temperature of a star, its chemical composition, how fast it is rotating, and, most relevant tonight, how fast it is moving away from us, and therefore how far away it sits. The key to all of this is the way light behaves as a wave. Light travels as a wave, oscillating through space at a fixed speed. The distance from one wave crest to the next is called its wavelength, and it is wavelength that determines color. Red light has a longer wavelength than blue light. Violet light has the shortest wavelength visible to the human eye. Infrared radiation, which we feel as heat, has wavelengths longer than red. Ultraviolet, which causes sunburn, has wavelengths shorter than violet. The entire range, from radio waves at the longest to gamma rays at the shortest, is called the electromagnetic spectrum, and visible light occupies only a narrow sliver of it. When a source of light is moving away from you, the waves it emits are stretched. Each successive wave crest is emitted from a position slightly farther away than the last, so by the time each crest reaches you, it has had to travel a little farther, and the effective wavelength you receive is longer than the wavelength at which it was emitted. This is redshift, the stretching of light toward the red end of the spectrum, and it is the direct observational signature of recession. Now here is where the expanding universe introduces something subtler and more interesting than ordinary Doppler shift. When a galaxy is receding because it is moving through space, like a car driving away from you, the redshift comes from the motion. The faster the motion, the greater the shift. But when a galaxy is receding because the space between you and it is expanding, the redshift comes from something different. It comes from the stretching of the light wave itself during its journey. Picture a light wave leaving a distant galaxy. It sets off on its journey with a particular wavelength. Let us say it is emitted as blue light. Over the millions or billions of years it takes to cross the expanding universe and reach us, the space it is traveling through is itself growing. The wave is embedded in that space, and as the space stretches, the wave stretches with it. By the time it arrives at our telescopes, the wavelength has been extended. What left as blue may arrive as red. The light has not Doppler shifted in the traditional sense. It has been cosmologically redshifted, physically stretched by the expansion of the space it was traveling through. The amount of stretching depends on how much the universe has expanded since the light was emitted. A galaxy whose light has been redshifted by a factor of 2 is one whose light was emitted when the universe was half its current size. A galaxy redshifted by a factor of 10 is one whose light left when the universe was 1/10 its current scale. Redshift, in this sense, is not just a velocity measurement. It is a record of cosmic history, a direct measure of how much the universe has grown since that light began its journey. This is how astronomers read expansion. They take the spectrum of a distant galaxy, identify the characteristic fingerprint patterns of known elements. Hydrogen is particularly useful with its distinctive series of spectral lines, and measure how far those patterns have shifted toward the red. The size of the shift tells them the redshift value, which tells them how much the universe has expanded since the light was emitted, which tells them the distance. And this brings us to the Hubble, Lemaitre law. The relationship that Hubble observed and Lemaitre had theoretically anticipated. For every additional 3.25 million light-years of distance, a galaxy appears to recede roughly 70 kilometers per second faster. A galaxy 3.25 million light-years away recedes at about 70 kilometers per second. One 6.5 million light-years away recedes at about 140 kilometers per second. One 1 billion light-years away recedes at something like 20,000 kilometers per second. The relationship is linear, and the constant of proportionality, that 70 kilometers per second per 3.25 million light-years, is the Hubble constant, the single number that encodes the current expansion rate of the entire universe. Measuring the Hubble constant accurately requires measuring two things: the recession velocity of a galaxy, which the redshift gives you directly, and its distance, which is considerably harder. The redshift is easy. You just need a spectrum. The distance requires what astronomers call a distance ladder, a sequence of overlapping methods, each calibrated against the one below it, that together allow measurements to be extended across the observable universe. The first rung of the ladder is geometric. For nearby stars, you can measure distance by parallax, the apparent shift in a star's position against the background when observed from opposite sides of Earth's orbit. This works out to distances of a few thousand light-years, using instruments like the European Space Agency's Gaia satellite, which has measured the positions and distances of over 1 billion stars with extraordinary precision. The second rung is the Cepheid variables that Henrietta Swan Leavitt identified. As we explored in the first chapter, these pulsing stars have a period luminosity relationship. Pulse rate reveals true brightness, and comparing true brightness to apparent brightness gives distance. Cepheids can be seen out to tens of millions of light-years, far enough to reach the nearest galaxy clusters. But tens of millions of light-years is still a small fraction of the observable universe, which extends some 46 billion light-years in every direction. To reach farther, astronomers use a third rung, a class of stellar explosions called Type Ia supernovae. A Type Ia supernova occurs in a binary star system, two stars orbiting each other, where one of the stars is a white dwarf, the dense remnant left behind when a sun-like star exhausts its fuel and sheds its outer layers. White dwarfs are made almost entirely of carbon and oxygen, held up not by nuclear burning, but by a quantum mechanical pressure, a pressure that arises because electrons, by the rules of quantum mechanics, resist being compressed into the same state as one another. This resistance is called electron degeneracy pressure, and it is what keeps a white dwarf from collapsing under its own gravity. But electron degeneracy pressure has a limit. There is a maximum mass, roughly 1.5 times the mass of our Sun, a threshold that physicists call the Chandrasekhar limit after the astrophysicist who calculated it, beyond which the pressure cannot hold. If a white dwarf accretes enough material from its companion star to approach this limit, it becomes unstable and explodes in a thermonuclear detonation of extraordinary violence. The explosion is so consistent because it always occurs at roughly the same mass threshold that Type Ia supernovae always reach approximately the same peak brightness. They are what astronomers call standard candles. You know how bright they truly are, and by measuring how bright they appear from Earth, you can calculate how far away they are. Billions of light-years away, across much of the observable universe. It was this third rung of the distance ladder, Type Ia supernovae, that enabled the most significant discovery in cosmology since Hubble's original observation, and we will come to that discovery in a later chapter because it changed everything about how we understand the future of the universe. For now, the picture is this. The universe is expanding measurably and consistently in every direction. Every galaxy beyond our local gravitationally bound neighborhood is receding from us, carried away by the growth of space itself. The light those galaxies emit is stretched during its journey, arriving redder than it left. And by reading that redness, by comparing it to the known brightness of standard candles, by climbing rung by rung up the distance ladder, astronomers have measured the rate of that expansion with increasing precision and have found, encoded in a single number, the heartbeat of the cosmos. We have been moving backward in time, tracing the expansion of the universe toward its origin. Hubble's observations implied that the galaxies were once closer together. Lemaitre's mathematics implied they were once compressed into something extraordinarily small and hot. Follow that thread far enough back and you arrive at a moment, or rather at a fraction of a moment, so early in the history of the universe that ordinary language struggles to describe it. The universe is approximately 13.5 billion years old. The Big Bang, in the conventional sense, the hot, dense, rapidly expanding early state, is where the standard cosmological story begins. But there is a chapter before that chapter, or rather within the very first instant of it, that cosmologists believe was responsible for shaping everything that came after. It is called cosmic inflation, and it is one of the most extraordinary ideas in all of science. To set the scale, the inflationary period is thought to have begun at something like 1/10,000 billionth of a second after the Big Bang, a number so small that writing it out in ordinary decimal form would require 36 zeros after the decimal point before you reached a non-zero digit. This is not a timescale that has any intuitive meaning. It is far shorter than anything a clock could ever measure. It is shorter than the time it takes light to cross a single atomic nucleus. It is a duration so brief it sits at the very edge of what physics can currently describe. And in that almost incomprehensibly brief interval, something happened that was even more extreme than the expansion we observe today. The universe expanded by a factor of at least 10 million, billion. That is a 1 followed by 25 zeros in every direction. A region of space far smaller than a single proton was inflated to a size larger than a grapefruit. In a fraction of a moment, the observable universe went from something unimaginably tiny to something at least the size of a marble and possibly much larger. This is the theory of cosmic inflation, first proposed by the physicist Alan Guth in 1980 and refined by many others since. Guth was not trying to explain expansion in general. He was trying to solve a specific set of puzzles that the standard Big Bang model left unanswered. One puzzle was called the flatness problem. The geometry of the universe, whether space is curved like the surface of a sphere, curved the other way like a saddle, or flat like a sheet, is determined by the total density of matter and energy. If the density is exactly at a certain critical value, the universe is flat. The observations show that the universe is, to extraordinary precision, flat. But a flat universe is an unstable configuration in the standard model, like a pencil balanced on its tip. Any small deviation from perfect flatness in the early universe would have been amplified over time into a very curved universe today. The fact that the universe is so flat implies that in the very early universe, the density was tuned to the critical value with a precision of at least 1 part in 10 to the power of 60. That is not impossible, but it is deeply unsatisfying. It demands an explanation. Another puzzle was the horizon problem, the cosmic microwave background, the ancient glow of radiation from the early universe, which we will explore in the next chapter, has the same temperature in every direction to a precision of 1 part in 100,000. Regions of the sky on opposite sides of us, separated by tens of billions of light years, have the same temperature. But in the standard Big Bang model, those regions could never have been in contact with each other. They were too far apart for light to have traveled between them in the time available. How, then, did they come to be at the same temperature? How did they agree? Inflation solves both problems elegantly. If the entire observable universe was once a tiny, causally connected region, small enough for everything within it to have exchanged energy and come to a common temperature, and then that region was inflated by an enormous factor, the resulting large-scale universe would naturally appear uniform in temperature. And the flatness problem dissolves too, because inflation stretches any initial curvature out so dramatically that the resulting universe appears flat to any observer within it, just as the surface of a balloon, once inflated enormously, appears flat to an ant walking on it. What drove inflation? The leading idea involves a theoretical energy field called the inflaton field that permeated the newborn universe. Fields in physics are not mysterious. A gravitational field, for instance, is simply a description of the gravitational influence at every point in space. The inflaton field is hypothesized to have had a very high energy density in the early universe, and the particular way it interacted with space, a kind of negative pressure, a repulsion built into the field itself, drove the exponential expansion. As inflation proceeded, the field slowly lost energy, and when it dropped below a critical threshold, inflation ended. The energy stored in the field was released as an intense burst of radiation and particles, reheating the universe and launching the hot, dense phase we call the Big Bang proper. But inflation did something else, something that connects the physics of the very small to the structure of the very large in a way that is genuinely beautiful. In quantum mechanics, the physics of the very small, There is a principle, sometimes called the uncertainty principle, that states there is a fundamental, irreducible limit to how precisely you can simultaneously know certain pairs of properties of a system. You cannot know both the exact position and the exact momentum of a particle at the same time. More relevant here, you cannot have a region of space that is perfectly, exactly empty. Even in a complete vacuum, quantum mechanics demands that there are constant, unavoidable fluctuations in energy. Tiny, temporary deviations from zero, appearing and vanishing at random. These are called quantum fluctuations, and they are not a measurement problem or a limitation of our instruments. They are a fundamental feature of reality. Empty space is not truly empty. It is seething with these infinitesimal jitters. During inflation, those quantum fluctuations, ordinarily confined to scales far smaller than an atom, were caught up in the exponential expansion and stretched from the subatomic to the cosmic. A tiny random variation in energy density at one location, which would normally have appeared and vanished in an instant, was instead inflated to a scale millions of light years across. By the time inflation ended, the universe was not perfectly uniform. It was peppered with slight variations in density, regions marginally denser than average, regions marginally less dense, at scales spanning the entire observable cosmos. These variations were tiny. We are talking about differences of roughly 1 part in 100,000, but they were enough, because gravity is patient. In the slightly denser regions, gravity pulled matter together a little more strongly. Over millions of years, those regions accumulated more matter. Over hundreds of millions of years, the first stars ignited within them. Over billions of years, galaxies formed, then clusters of galaxies, then the vast filaments and sheets and voids that make up what astronomers call the cosmic web, the large-scale structure of the universe, a three-dimensional tapestry of matter with galaxy clusters at the intersections and enormous empty voids in between. Every galaxy you have ever seen in a photograph, every cluster of galaxies, every filament of the cosmic web, every star, every planet, every ocean, every mountain, every living thing. All of it traces its origin to a quantum fluctuation, a random jitter in the energy of empty space. That was stretched to cosmic scale in the first fraction of the first second of time, and then slowly, patiently, under the influence of gravity, grew into structure. There is something deeply moving about this, if you let it settle. The largest structures in the universe have their roots in the smallest possible events. The cosmic and the quantum are not separate realms. In the first instant of time, they were the same thing. The universe we inhabit today is, in a very real sense, a quantum fluctuation writ large. The theory of inflation remains just that, a theory, not yet directly confirmed. There is no single piece of observational evidence that proves inflation happened, but there are many pieces of evidence consistent with it, and the problems it solves are real. The flatness of the universe, the uniformity of the microwave background, the particular pattern of density variations imprinted across the sky, all of these are predicted by inflationary models, and all of them are observed. The details of inflation, exactly when it happened, what the inflaton field was, precisely how long it lasted, are still being worked out. But the broad picture has become a central pillar of modern cosmology, and the idea at its heart is one of the most extraordinary in science, that the large-scale structure of the universe was seeded by the quantum noise of the void. If you could build a radio antenna sensitive enough and point it at any patch of the sky, any direction at all, you would detect a faint, persistent signal, not from a star, not from a galaxy, from everywhere at once. A gentle, ancient hiss, arriving equally from all directions, carrying information about a moment nearly 14 billion years ago. This signal is called the cosmic microwave background, and it is one of the most extraordinary things in the observable universe. Its discovery was an accident. In 1964, two radio astronomers working at Bell Telephone Laboratories in New Jersey, Arno Penzias and Robert Wilson, were calibrating a large horn-shaped antenna that had been built for satellite communication. They were trying to account for all the sources of noise in their system, and they kept finding a residual signal they could not explain. It was not coming from any identifiable source. It was not coming from New York, which they initially suspected might be contributing radio interference. It was not coming from the pigeons that had nested in the antenna and coated the interior with what the physicists diplomatically described as a white dielectric material, which they cleaned out carefully, and still the signal remained. It came from every direction with equal strength, regardless of where they pointed the antenna, regardless of what time of day or year they measured it. It was isotropic, the same in all directions, to a degree that suggested it was not a local phenomenon at all, but something cosmic. Meanwhile, a group of theoretical physicists at Princeton University, led by Robert Dicke, had independently predicted that if the universe began in a hot, dense state and had been expanding and cooling ever since, there should be a remnant glow of radiation permeating all of space, cooled by the expansion to a temperature of just a few degrees above absolute zero, and therefore detectable as microwave radiation. Dicke's group was actually building an instrument to search for it when they heard about Penzias and Wilson's unexplained signal. They arranged a meeting, compared notes, and quickly understood what had been found. To understand why this glow exists and what it can tell us, you need to picture the early universe in some detail. In the first few 100,000 years after the Big Bang, the universe was unimaginably hot and dense, not hot enough for matter as we know it to exist in stable form. Atoms could not hold together. Any electron that tried to bind to a proton was immediately knocked away by the intense thermal energy of the surrounding radiation. Instead, matter existed as a plasma, a seething mixture of free electrons, free protons, and photons of light, all interacting intensely with one another. The photons could not travel freely. Every time a photon tried to move, it almost immediately scattered off a free electron and changed direction. The universe was opaque, the way a dense fog is opaque. Light could not escape. It was trapped. This situation persisted for roughly 380,000 years. Then something changed. As the universe expanded, it cooled. The temperature dropped. And at a certain critical temperature, roughly 3,000 degrees, comparable to the surface of a cool star, something happened to the electrons. They slowed down enough that protons could capture them. Electrons settled into stable orbits around protons, forming the first hydrogen atoms. This moment is called recombination, not because it happened before, but because it is the moment electrons and protons first combined into atoms. With the electrons no longer free, the photons suddenly had nothing to scatter off. The universe became transparent. The fog lifted. Light could travel freely for the first time, streaming outward in all directions, carrying with it an imprint of the state of the universe at that moment. Those photons had been traveling ever since, for nearly 14 billion years, through an expanding universe, and as they traveled, the expansion of space stretched their wavelengths. What began as the glow of a 3,000-degree plasma, visible light, and infrared radiation has been stretched by a factor of about 1,000 into microwave radiation, corresponding to a temperature of just under 3 degrees above absolute zero. That is the signal Penzias and Wilson detected. The cooled, stretched, ancient light of the moment the universe first became transparent. The cosmic microwave background is not a signal from a distant location. It is a signal from a distant time, arriving from all directions because the moment of recombination happened everywhere at once. Every patch of the sky, when you look at microwave wavelengths, is showing you the same surface. The last scattering surface, astronomers call it, the boundary in time beyond which the universe was opaque and light could not escape. It is as far back as we can see with electromagnetic radiation. For decades after its discovery, the microwave background appeared perfectly uniform, same temperature in every direction, to extraordinary precision. But theorists predicted there should be tiny variations, echoes of the density fluctuations seeded by inflation, imprinted on the plasma at the moment of recombination. Regions slightly denser than average would be very slightly hotter, less dense regions slightly hotter, less dense regions slightly cooler. The variations would be tiny, about 1 part in 100,000, but they should be there. Finding them required instruments of extraordinary sensitivity. In 1992, the COB satellite, the Cosmic Background Explorer, detected the variations for the first time, and the cosmology community was electrified. The variations were exactly the kind expected from inflation, at exactly the scale expected. It was, as the physicist George Smoot described it at the time, like seeing the face of God, a phrase that caused some controversy but conveyed the sense of awe felt by the researchers involved. Subsequent satellites refined the picture with increasing precision. The WMAP satellite, operating in the early 2000s, mapped the temperature variations across the full sky with far greater detail. Then the Planck satellite, operated by the European Space Agency and completing its primary mission in 2013, produced what remains the most precise map of the cosmic microwave background ever made. A full-sky portrait of the universe at 380,000 years of age, with temperature variations measured to a precision that allowed cosmologists to extract an extraordinary amount of information about the universe's composition, geometry, and history. The pattern of hot and cold spots in the Planck map is not random. It has a characteristic structure, a statistical distribution of sizes and intensities that is the direct imprint of the acoustic oscillations in the primordial plasma. When the universe was a hot plasma, the competing forces of gravity, which tried to pull matter together into denser clumps, and radiation pressure, which pushed outward like sound waves, set the plasma ringing like a struck bell. These oscillations, called baryon acoustic oscillations, left a specific pattern of density variations at recombination, and that pattern is visible in the microwave background today. By analyzing the precise pattern of those temperature variations, their sizes, their relative intensities, their statistical properties, cosmologists can determine the age of the universe, the fraction of it made up of ordinary matter, the fraction made up of dark matter, the fraction made up of dark energy, the geometry of space, and the expansion rate. All of this from a faint ancient glow of microwaves. The numbers the Planck satellite extracted are precise and consistent. The universe is 13.8 billion years old to a precision of about 1%. Ordinary matter, the atoms that make up stars, planets, and everything you have ever touched, constitutes just under 5% of the total energy content. Dark matter, which does not emit or absorb light, but exerts gravitational influence, makes up about 27%. And dark energy, which we will come to in the next chapter, accounts for the remaining 68%. The universe is, in its dominant composition, made of things that are invisible to us. Ordinary matter is a minority constituent of a cosmos mostly made of mystery. And at the heart of all of this, the temperature map, the acoustic oscillations, the precise numbers, are the quantum fluctuations from inflation, stretched and frozen and imprinted on the plasma of the early universe, then carried forward on ancient light to our instruments today. The microwave background is, in a very real sense, a photograph of the quantum origins of everything. For most of the 20th century, a central assumption of cosmology went largely unquestioned. Gravity, acting on all the matter in the universe, must be slowing the expansion down, not stopping it. The expansion was clearly real. Hubble had established that, but decelerating it, the way a ball thrown upward slows as it rises. The question was not whether the expansion was decelerating, but by how much. Was there enough matter in the universe for gravity to eventually halt the expansion and pull everything back together in a distant future collapse? Or was the universe too sparse, and would it expand forever, but ever more slowly? Either way, the deceleration was assumed. It was physics. Gravity pulls things together. Of course it was slowing down. In the late 1990s, two independent teams of astronomers set out to measure that deceleration. They used Type Ia supernovae as their standard candles, those stellar explosions that always reach roughly the same peak brightness, and therefore serve as reliable distance markers across billions of light years. The idea was straightforward. By observing supernovae at very large distances, you are looking at them as they were billions of years ago, when the universe was younger. If the expansion was decelerating, then the universe was expanding faster in the past than it is now. That means the distances to those ancient supernovae would be slightly smaller than you would expect if the expansion rate had stayed constant. The universe had less time to grow before the light left, so the supernovae would appear slightly brighter than a constant rate model would predict. Both teams made their measurements. Both teams compared the observed brightness of their distant supernovae to the predictions, and both teams found something that contradicted everything they expected. The distant supernovae were not slightly brighter than expected. They were slightly dimmer. They were farther away than a decelerating universe would place them. The universe was not expanding more slowly than in the past. It was expanding faster. The expansion was not decelerating. It was accelerating. The two teams, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees, initially distrusted their own results. Dimmer supernovae could, in principle, be explained by dust absorbing some of the light, or by the possibility that supernovae in the distant past were intrinsically dimmer than modern ones. The teams worked carefully to rule out these alternatives. They examined the spectra of the supernovae to check their composition. They looked for systematic effects. They cross-checked against other observations. The result held. The universe's expansion was speeding up. In 2011, Perlmutter, Schmidt, and Rees were awarded the Nobel Prize in Physics for the discovery. The question was immediate and obvious. What could possibly be causing the expansion to accelerate? Gravity decelerates. For the universe to be accelerating, something would have to be working against gravity at cosmic scales, a repulsive influence spread throughout space, stronger than the combined gravitational pull of all the matter in the universe. Something that was not matter. Something that was not radiation. Something that had no name. It was given one dark energy. The term is more of a placeholder than a description. Dark energy is not dark in the way dark matter is dark, meaning invisible but gravitationally detectable. Dark energy is dark in the sense that we have almost no idea what it is. We know it exists because of its effects. We know it constitutes approximately 68% of the total energy content of the universe, making it by far the dominant component. We know it has a repulsive effect on space, and beyond that, the honest answer is that we do not know much. The leading theoretical idea treats dark energy as a property of space itself, an energy inherent to the vacuum, present everywhere and at all times, with a fixed density per unit volume. This is essentially what Einstein's cosmological constant described, the term he inserted to hold the universe still and later removed in embarrassment. It turns out the cosmological constant was not a blunder. It was, in a sense, a prediction, just not of the effect Einstein intended. The energy of the vacuum, if it exists, would behave exactly as dark energy is observed to behave. Here is why this energy causes acceleration and why that effect grows over time. Ordinary matter has a gravitational effect that decreases as the universe expands. As the galaxies spread out, the matter becomes more dilute and its gravitational influence weakens. Dark energy, on the other hand, if it is a property of space itself, does not dilute. As space grows, the amount of dark energy grows proportionally. more space, more vacuum energy. So as the universe expands, the gravitational influence of matter weakens, while the repulsive influence of dark energy stays constant or even grows. At some point, and this transition happened roughly 4 billion years ago, when the universe was about 2/3 of its current age, the balance tipped, dark energy became dominant. The expansion, which had been decelerating, began to accelerate, and it has been accelerating ever since. The density of dark energy is extraordinarily low, roughly 7 times 10 to the power of -30 grams per cubic centimeter. That is an almost incomprehensibly small amount per unit volume. But space is vast, and that tiny density, integrated across the entire observable universe, amounts to an enormous total energy, more than sufficient to overcome the gravitational attraction of all the matter that exists. There is a deep puzzle lurking here, though, that physicists find genuinely troubling: quantum field theory. The framework that describes particles and forces at the subatomic level also predicts that the vacuum should have an energy. But when you calculate what that energy should be, using the best available theory, you get a number that is roughly 120 orders of magnitude larger than the observed value of dark energy. That is not a small discrepancy. That is the largest discrepancy between a theoretical prediction and an observation in the history of science. Something is clearly missing from our understanding. Either quantum field theory is wrong about the vacuum energy, or there is some unknown mechanism that cancels almost all of it, leaving only the tiny residue we observe. No one knows which. No one knows how. An alternative possibility is that dark energy is not a fixed property of space, but a dynamic field, something that changes over time and varies from place to place, more like the inflaton field of the early universe than a simple constant. This idea is sometimes called quintessence, a field that slowly evolves, meaning the dark energy density and its repulsive effect might be different today than they were in the past, and different again in the future. Recent data from the Euclid Space Telescope and other surveys have begun to hint, tentatively, that dark energy may not be perfectly constant, that it might be changing slowly over cosmic time. The evidence is not yet conclusive, but it is being watched carefully. What is clear is this: the universe is mostly made of something we cannot see, cannot sample, cannot directly detect, and do not understand. Ordinary matter, atoms, molecules, the stuff of stars and planets and living things, is a 5% minority in a cosmos dominated by dark matter and dark energy. The universe as we experience it, the visible, tangible, luminous universe, is the foam on the surface of a much deeper and more mysterious ocean. And that ocean is expanding, accelerating, carrying the visible universe with it into a future that will look very different from the present. Science is not a collection of settled facts. It is a living process, and one of the signs that it is working is the appearance of a genuine, stubborn disagreement between measurements that should agree. A crack in the current understanding that resists being smoothed over, that grows sharper rather than softer as the instruments improve. Right now, in cosmology, there is exactly such a crack. It is called the Hubble tension, and it is one of the most significant open questions in contemporary science. The Hubble constant, the number that describes how fast the universe is currently expanding, can be measured in 2 fundamentally different ways. Each method is rigorous, each has been refined over decades, and each is now precise enough that the results should match. The first method works backward from the early universe. The cosmic microwave background, as we explored in the previous chapter, carries within its temperature variations a detailed record of the conditions at recombination, 380,000 years after the Big Bang. By fitting a theoretical model, the standard lambda CDM model, which describes a universe composed of ordinary matter, dark matter, and a cosmological constant for dark energy. To the precise pattern of those temperature variations, cosmologists can determine all the parameters of the universe, including the Hubble constant. The Planck satellite's analysis of the microwave background yields a Hubble constant of approximately 67 kilometers per second per megaparsec, where a megaparsec is about 3.25 million light-years. The second method works forward from observations of the local universe. Astronomers measure distances to nearby galaxies using Cepheid variables, calibrate those distances against Type Ia supernovae, and use the supernovae to measure the recession velocities of more distant galaxies. This distance ladder approach, applied by teams using the Hubble Space Telescope and then refined using the James Webb Space Telescope, consistently returns a Hubble constant of approximately 73 kilometers per second per megaparsec, roughly 8 or 9% higher than the early universe value. 8 or 9% sounds small, but both measurements now have error bars small enough that the gap between them is statistically significant, not a matter of measurement uncertainty, but a genuine reproducible discrepancy. In science, a result that is 5 standard deviations away from expectation, what physicists call a 5 sigma discrepancy, is conventionally considered a discovery discrepancy. The Hubble tension has reached that level. It is not noise, it is a signal. The James Webb Space Telescope, launched in December 2021 and beginning science operations in 2022, was hoped by many to resolve the tension. Its larger mirror and infrared sensitivity allow it to observe Cepheid variables in galaxies farther away than Hubble ever could, with less contamination from crowded stellar fields. The expectation, or at least the hope, was that the improved measurements would show the local universe value drifting down toward the early universe value, revealing some systematic error in the previous work. Instead, when the Webb results came in, they confirmed the Hubble Space Telescope's numbers. The local universe expansion rate remained stubbornly high. The tension did not dissolve. If anything, it deepened. The problem was not in the instruments. The discrepancy was real. So, what might explain it? There are several possibilities, and all of them are interesting, because all of them require something beyond the standard model of cosmology. One class of explanation involves the early universe. The early universe measurement of the Hubble constant depends on the model used to interpret the microwave background data. If that model is missing something, some ingredient that was present in the early universe but has not been accounted for, then the derived Hubble constant would be wrong. One specific proposal involves hypothetical new particles, sometimes called early dark energy, that would have contributed a small additional energy density to the universe in the first few 100,000 years, altering the acoustic oscillations in the plasma and shifting the derived expansion rate upward. Several versions of this idea have been proposed and tested against the data, with mixed results. None has emerged as a clear solution, but none has been definitively ruled out. Another possibility is that dark energy is not constant. If the repulsive energy of the vacuum changed over cosmic time, higher in the past, lower now, or the reverse, then the expansion history of the universe would differ from what the standard model assumes, and measurements derived from different epochs might genuinely reflect different effective expansion rates. Some recent observational hints from Galaxy surveys suggest dark energy may be evolving, though the evidence remains preliminary. A more radical possibility is that Einstein's general relativity itself, while exquisitely accurate on the scale of the solar system and well tested on many other scales, may need modification at the scale of the entire universe. There are alternative theories of gravity, modifications to general relativity that introduce additional terms or fields that can, in principle, alter the expansion history in ways that relieve the Hubble tension. These theories are difficult to construct without introducing other problems, and none has yet emerged as a compelling replacement for general relativity. But the tension gives theorists a concrete target to aim at. There is also the possibility of a flaw in the distance ladder itself. not an instrumental error, but a conceptual one. The latter rests on the assumption that Cepheid variables in distant galaxies behave the same way as those in nearby galaxies used for calibration. If there are subtle, systematic differences in the chemical composition of the stellar populations or in the environments of the galaxies, then the distances derived from Cepheids might be systematically off, and the local Hubble constant would be wrong even if the measurements themselves are precise. This possibility has been investigated carefully, and the Webb observations were partly designed to test it. The investigation continues. What the Hubble tension represents at its heart is a genuine confrontation between two precise measurements that disagree. In science, this is not a failure, it is an opportunity. The history of physics is full of moments when a small, stubborn discrepancy between theory and observation turned out to point towards something new and important: the anomalous orbit of Mercury that general relativity explained, the ultraviolet catastrophe and black body radiation that quantum theory resolved. The Hubble tension may be pointing towards something similarly significant: new particles, new physics, a modification of our understanding of dark energy, or a revision of our theory of gravity at the largest scales. The answer is not yet known. That is what makes this moment in cosmology genuinely exciting, even as it is genuinely uncertain. The universe is telling us something. We have not yet understood what. Follow the expansion forward. Not just a few billion years, but much farther, into the deep future where the timescales become almost impossible to hold in mind and where the universe looks nothing like the one we inhabit now. The universe today is rich. It is rich with light. Hundreds of billions of galaxies, each containing hundreds of billions of stars, scattered across a volume so vast that the light from the most distant ones takes tens of billions of years to reach us. It is rich with structure, the cosmic web of filaments and clusters, the gravitationally bound groups of galaxies like our own local group, which contains the Milky Way, the Andromeda Galaxy, and a few dozen smaller companions. It is rich with the possibility of new stars being born, old stars dying, planets forming, complex chemistry developing in the cold between the stars. But this richness is not permanent. It is a feature of this particular era, this particular moment in cosmic history. And the expansion, accelerating as it is under the influence of dark energy, is slowly working to end it. The mechanism is straightforward, and it follows directly from what we have already explored. Space is expanding. The farther a galaxy is from us, the faster the space between us grows. At a certain distance, called the Hubble radius, roughly 14 billion light-years today, the space between us and a galaxy is already expanding at the speed of light. Galaxies beyond that distance are receding faster than light can travel, which means light they emit now will never reach us. They are, in a sense, already beyond our reach, already hidden behind what cosmologists call the cosmic event horizon. Not a physical boundary, but a limit in time, a point beyond which no information can ever cross to us. As the acceleration continues, this horizon moves inward. Galaxies that are currently just within our reach, just close enough for their light to eventually arrive, will gradually cross the threshold. Their light will be redshifted further and further, stretched toward longer and longer wavelengths, growing fainter and fainter, until it fades below any possible detection. One by one, over hundreds of billions of years, the galaxies will disappear, not because they have been destroyed, not because they have moved through space past some wall, but because the space between us will be expanding faster than light can cross it, and their signals will never arrive. The local group, our own gravitationally bound neighborhood, will be exempt from this dispersal. Gravity, within a bound group, is strong enough to hold the galaxies together against the expansion of space. The Milky Way and Andromeda are actually approaching each other and are expected to merge in roughly 4 billion years, forming a single larger galaxy. The other members of the local group will eventually merge with it too. This merge system will remain bound, an island of matter in an increasingly empty universe. But beyond the local group, the universe will grow quiet. On timescales of 100 billion years or so, all the galaxies outside our gravitationally bound neighborhood will have receded beyond the event horizon. An observer in the far future, looking out from the merged remnant of our local group, will see an apparently empty sky. No other galaxies. No cosmic web. No evidence from direct observation that any other galaxies ever existed. The universe will look from the outside like a single isolated island of matter surrounded by an infinite, featureless, expanding void. And then, over timescales that dwarf even that, trillions and then quadrillions of years, the stars within that island will slowly exhaust their fuel. The most massive stars burn out first, within millions of years. Sun-like stars have lifetimes of billions of years. But the smallest, most frugal stars, the red dwarfs, burn so slowly and so carefully that they can persist for trillions of years, glowing dimly in the dark. Eventually, though, even they will fade, one by one. The stars will go out. The universe will become a cold, dim collection of stellar remnants. White dwarfs cooling slowly toward black, neutron stars spinning down over unimaginable timescales, and black holes, patient and vast, slowly evaporating over periods so long they make the current age of the universe look like an instant. Physicists believe that black holes are not truly permanent, a process described theoretically by Stephen Hawking called Hawking radiation, a quantum mechanical effect by which black holes very slowly emit energy and gradually lose mass, means that even the largest black holes will eventually evaporate completely, over timescales of perhaps 10 to the power of 100 years. After that, there is nothing left but a very cold, very diffuse gas of elementary particles, photons and electrons and their antiparticles spread through an enormous and still expanding void. No structure, no gradients, no information. Just a slow, cold, even distribution of almost nothing, expanding forever. This is the far future of the universe. If our current understanding is correct, it is not a fate that threatens anyone alive today, or anyone who will ever live. It is remote beyond any human sense of time. But it is worth knowing, because it gives context to the present moment, and the present moment, seen from this perspective, is extraordinary. We exist at a very particular time in cosmic history. The universe is 13.5 billion years old. It will persist for trillions of times longer. We are, in cosmic terms, early. We live in the era when the universe is still young enough to be making new stars, still rich enough to be full of galaxies, still transparent enough that we can see the ancient microwave background and read the history of the universe's first moments. All of these things are temporary features of an early epoch. In the deep future, none of them will be available. An observer in 1 trillion years, if such a being could exist, would have no way to know the universe had once been full of galaxies. The galaxies would be gone, beyond the horizon, their signals long since faded. There would be no cosmic microwave background detectable. It would have been stretched to wavelengths so long they would be unobservable. There would be no Cepheid variables, no supernovae, no distance ladder. There would be no way to measure the Hubble constant, because there would be nothing to measure it with. The evidence for the Big Bang, for inflation, for expansion itself would be inaccessible. The universe would be a closed book. We are here in the chapter when the book is open. Everything we have explored tonight, Slipher's patient measurements at Flagstaff, Leavitt's insight about the pulsing stars, Hubble's photographs on Mount Wilson, Penzias and Wilson's inexplicable hiss, the Planck satellite's portrait of the ancient plasma, the dimmer-than-expected supernovae of the 1990s, the stubborn tension in the Hubble constant, all of this has been possible because we exist in this particular window of constant. All of this has been possible because we exist in this particular window of cosmic time. a window in which the universe is old enough to have formed stars and galaxies and planets and the chemistry of life, but young enough that the evidence of its origin and its history is still written across the sky in light. It will not always be so. The window is open now. We are looking through it now. And there is something quietly steadying in that thought. Whatever you are carrying tonight, the weight of the day, the noise of the world, the things that felt large and pressing in the hours before you lay down, all of it sits within this moment, this window, this brief and luminous era in the life of a universe that has been expanding since before time had any meaning we could attach to it. You are not separate from that expansion. You are part of it. The atoms in your body were forged in stars that have since died, scattered by stellar winds across the galaxy, gathered by gravity into a planet, and eventually into you. You are made of the universe. You are an expression of it, a temporary arrangement of its matter in a form complex enough to look up and wonder about its own origins. Space is still stretching. Right now, as your breathing slows and the thoughts grow quieter, the galaxies are drifting gently apart, not rushing, not colliding, just slowly, steadily, carried by the growth of space itself, moving apart in the vast and patient dark. It has been happening for nearly 14 billion years. It will continue long after the last star has faded. It asks nothing of you. It requires no response. It is simply happening, enormous and unhurried, in every direction at once. You are held within it, small and brief and real, drifting alongside everything else into the long and gentle future. And so we leave it there, somewhere behind you. The day has already grown distant. The universe is still expanding, soft and slow in the dark. Drift now if you're ready. Sleep well.